Okay, so you have learned about complex numbers before. These are when we have imaginary numbers as part of a number. And I is the square root of -1. And then remember, because of that, I squared is -1. So a complex number is in the form a plus bi, where a is the real part and bi is the imaginary part. If b isn't 0, then the whole number is called an imaginary number. And if you only have the bi part, it's called a pure imaginary number. Then when we're working with radicals, we always write the I before it so we don't get confused and think the I is part of the number under the radical. So on number 1, it wants me to perform the indicated operations and write the result in standard form. These are pretty much like combining like terms with numbers and variables when I'm adding and subtracting. So I have a 5 and a 7 that get added together. That gives me 12. Then I have -11 and positive 4i. That gives me -7i. On the subtraction one, I want to go ahead and distribute that negative all the way through. So I have -5i from the first part. Then I have plus 11 plus 6i. And then I can combine my like terms. So I have -5 plus 11, which gives me 6i, plus 6i, which gives me 7i. Okay. On number 2, we are multiplying. So on this one, I'm just distributing. I have 12i. And then -20i squared. Whenever I have I squared, I want to turn it back into the -1. So I have 12i minus 20 times -1. Then I have 12i plus 20, because 2 negatives makes a positive, and then we need to always write this in standard form, so the real part always goes first. So I have 20 plus 2i. Over here on b, I'm going to FOIL like it's two binomials. So I have 7 times 2, which gives me 14. 7 times -5, which gives me -35i. -3i times 2 is -6i. -3i times -5i is positive 15i squared. So I'm going to combine like terms. So I have -35 minus 6i, which gives me -41i. Over here with the I squared, I'm going to rewrite that as a -1. Then I'm going to multiply the 15 by the -1. So I have 14 minus 41i plus 15. I don't know, it should be minus 15 now because I multiplied. Okay, then I want to combine like terms. I have a positive 14 and a -15, which gives me a -1 minus 41i. Okay, a complex conjugate is basically the same thing with just the middle sign changed. So instead of being a positive, it turns into a negative, and instead of being a negative, it turns into a positive. We use complex conjugates when we want to rationalize our denominators so we have a real number on the bottom. So if I take, and then we also can use these. Basically what it is I take the a value and square it and add it to the b value squared. Okay. So over here, my complex conjugate is 2 plus 5i. So then I want to multiply on the top. I have 7 times 2, which gives me 14. 7 plus 5i, which gives me 35i. 4i times 2, which gives me 8i. 4i times 5i, which gives me 20i squared. On the bottom, because they are opposite signs, I can use the difference of squares formula. So I have 2 squared, which is 4. Minus 5i squared, which is 25i squared. Okay. Then I want to rewrite. On my top, I have 14 plus 43i plus 20 times -1. On the bottom, I have 4 minus 25 times -1. Then I want to rewrite. On the top, I have 14 plus 43i minus 20 over 4 plus 25. Then I combine like terms. I have -6 plus 43i on the top, 29 on the bottom. When I'm working with imaginary numbers, I want to split it up into two numbers because I have to have the real part and the fake part. I mean the imaginary part. I have -6 over 29 and then 43 over 29i. Okay. So remember, because I is the square root of -1, I can change these to have an I and then simplify my radicals. So over here, I'm going to do a factor tree for 18. It's 2, 9, 3, and 3. So the pair of 3's can come out. And then I'm going to take out that negative with an I, and I'm left with square root of 2. I can do the same thing for 8. My factor tree is 2, 4, 2, and 2. So a pair of 2's can come out, and a 2 is left inside. Then I just combine the outside pieces, so I have 3i minus 2i, which just gives me I square root of 2. Over here on B, I want to rewrite it first. So I have negative 1 plus I square root of 5 squared. So then negative 1 times negative 1 is 1. Then I have negative I square root of 5, negative I square root of 5, plus I square root of 5 squared. Then I combine like terms. I have 1 plus, that shouldn't be a plus, it should be a minus. 2i square root of 5. And over here I have I squared and square root of 5 squared, so I have negative 1 times just 5, because the square root squared is the number on the inside. Then I still have 1 minus 2i square root of 5. Now it's minus 5, so 1 minus 5 is negative 4. Okay, over here on C, I want to factor tree 50. I have 2 and 25, 5 and 5. So 5 is going to be the number that goes outside. I have negative 25 plus 5i square root of 2 over 15. I'm going to split this up into two fractions. I have negative 25 over 15 plus 5 over 15i square root of 2. Then I can simplify my fractions. Negative 25 over 5 is negative 5/3. 5 over 15 is 1/3 I square root of 2. Okay. Then the last thing I have to teach you is DeMoivre's theorem. It's a pattern we use to turn complex numbers from polar to rectangular form. And when a number is in polar form, it'll have r as the radius and theta as a given angle. So these are the ones you've probably seen with the curly graphs that go around the origin. DeMoivre's theorem states that if z equals r times cosine theta plus I sine theta, and that's a complex number in polar form, then n is a positive integer. Z to the n power can be rewritten as r to the n times cosine n plus I sine n theta. So number 1 wants me to use this formula to write my answer in rectangular form. 2 is my radius, so I'm going to have 2 to the 6 cosine, and then I put in the exponent in front of my angle, so I'm going to have 6 times 20. And then because this is out in parentheses, the r to the n can also go in front of the I sign. So I have 2 to the 6 I sine 6 times 20. Okay, 2 to the 6 is 64. 6 times 20 is 120. And then I just need to evaluate these two trig functions at 120. 120 is in the second quadrant. Cosine will be negative. Its reference angle is 60. So cosine is negative 1/2. For sine, it'll be positive, and its reference angle is also 60, so it's square root of 3 over 2. Then I just need to simplify these two, and I've turned it back into rectangular form. So 64 times negative 1/2 is negative 32. 64i times square root of 3 over 2. I just divide 64 by 2, which gives me 32. I write the I, square root of 3. I can also do it when I'm given complex form numbers. I can also use the theorem when I'm given complex numbers in the form a plus bi. I can rewrite it into a polar form of r times cosine theta plus I sine theta. We use r as the square root of a plus b, and tangent is the value of a divided by b to find our angle. So in order to use the theorem, I need to find r and my angle. R is going to be the square root of 1 plus 1, because my a is 1 and my b is 1. So this is just square root of 2. Then I'm going to do tangent theta equals my a divided by b, so 1 divided by 1. Tangent is 1 at pi fourths. So then I'm going to go plug back into the formula at the top of the page, and I have my exponent was 8, so I have square root of 2 to the 8th power cosine times 8 times pi fourths, because the exponent goes in front of my angle, plus, before the I, square root of 2 to the 8 times I sine 8 times pi fourths. Okay. Square root of 2 to the 8th power is 16. Then I'm going to rewrite this. 8 times pi fourths is 2 pi. Over here, I have 16i sine 2 pi. If I look at a unit circle, 2 pi is right here, and I evaluate there. So 16, cosine of 2 pi is 1. Sine of 2 pi is 0. So what I do is I just multiply. I end up with 16. And this cancels out, so my final answer is just 16.